Good evening. Welcome to the February meeting of the Silicon Valley SIGGRAPH. Tonight, we will have a presentation on human pose estimation by Yuan from NVIDIA Research. I am Alex Giancarlo, chair of the chapter. Before we go to tonight's presentation, let me introduce you to our organization. Silicon Valley ACM SIGGRAPH is a chapter of the international organization ACM SIGGRAPH, which is the premier organization for professionals in the computer graphics field. Members come from both the technical as well as the artistic side. SIGGRAPH supports its members by providing opportunities for continued education, networking, and job hunting. Our local chapter continues the SIGGRAPH mission all year long on the local level. We typically meet at various Silicon Valley companies about once a month. Our meetings are great for networking and learning the latest technologies. We also have job announcements from time to time. Since COVID hit, we have been online. However, we hope to get back to normal meetings, in-person meetings eventually. Our chapter is entirely volunteer run. Let me introduce the volunteers who help put the meetings together. I am Alex Giancarlo, chair of the chapter for the year 22-23. Brent Simon is vice chair. Carl Anderson is treasurer. And Ken Turkowski is a member at large in our planning meeting group. Finally, this could be you in the future because we are always looking for volunteers. Officer positions are voluntary. However, there are several benefits to being a volunteer. It's a great way to network since you're putting together meetings for the speakers. And so you have a chance to interact with them, which is much better than just attending a meeting. You can also help organize meetings around your interests. Finally, it's always a fun group of people to work with. People ask what are the time requirements for being a volunteer. There are no time requirements, so each volunteer just gives what time they can, and that determines what events we can have. If you like what you see here, please consider joining us. If you want to join us, there are several ways to contact us. You can visit our website or our meetup, or you can contact us through our email. We also have a YouTube channel on which many of the past meetings have been recorded. For those of you watching this on YouTube, these links will be in the description below. If you want to find this information later, just go to Google and type in Silicon Valley SIGGRAPH into Google. Now let me tell you about some of the meetings we have scheduled in the area of VR for March. Both of these are joint meetings with San Francisco Bay Area ACM chapter. The first is human-centered design for VR training. The speaker will be Dr. Jason Gerald. Dr. Gerald is CEO of NextGen Interactions and lead VR advisor at XMod. The presentation is for VR creators and stakeholders that are seeking insight on how to define, design, and evaluate impactful training. This will be a joint meeting hosted by SF Bay ACM. The date will be Wednesday, March 15th. The second meeting will be Improving VR AR Experiences by Understanding the Human Visual System. The speaker will be Brooke Krajanich, who is a final year PhD candidate in the Electrical Engineering Department at Stanford University. This presentation describes two different ways in which a greater understanding of the human visual system may assist in achieving the goal of providing perceptually realistic user experiences, while constrained by limited compute budgets, hardware, and transmission bandwidth of wearable systems. We will host this joint event along with SF Bay ACM. The date will be Wednesday, March 29th. Please visit our meetup for more details about these meetings. I would now like to invite Ken to introduce tonight's speaker.
Hello, and welcome to February's presentation on human pose estimation. Human pose estimation has been plagued by noise and interpenetration and unrealistic kinds of behaviors. Yuan, our speaker today, is applying generative models and physics simulation to overcome these defects and produce much more natural motions. It can also reconstruct motions, plausible motions that have not been adequately observed, and well, and it gives much better results. Yuan is a research scientist at NVIDIA. He received his PhD in robotics from Carnegie Mellon in 2022, where he worked with Professor Chris Catani. His research lies at the intersection of computer vision, robotics, and machine learning. He's particularly interested in simulation, reinforcement learning, 3D computer vision, generative models, embodied agents, and digital humans. He's a recipient of the Qualcomm Innovation Fellowship and the NVIDIA Graduate Fellowship. He has collaborated with Disney Research and Facebook Reality Lab through internships. He's gotten his master's in computer science from Carnegie Mellon and bachelor's from Zhejiang University. Yay, take it away.
Cool, yeah, thanks for the introduction. Hello, everyone. Today, I will talk about improving human pose estimation with generative models and physics simulation. Before delving into the topic of human pose estimation, I'd like to provide some context by discussing a broader topic, human behavior modeling. So why do we want to model human behavior? The answer is simple. Many applications that involve humans require effective human behavior modeling. This includes AR, VR, where realistic human behavior is essential for immersive experiences. Animation and gaming, where natural character movement is crucial for creating engaging and lifelike experiences. Also, autonomous driving, where understanding and predicting human behavior can help improve safety and efficiency on the road. And finally, assistive robots, where modeling human behavior is necessary to enable robots to understand and interact with humans in a natural and safe way. Human pose is an essential aspect of human behavior model. Yeah, so we talked about human behavior modeling can have a lot of impact on these several different applications. And human pose is an essential part of human behavior modeling. It is useful for many of these applications, and it is also fundamental to tasks like action recognition and behavior forecasting. There are three essential aspects of human behavior modeling. The first one is perception, which aims to understand human behavior from visual inputs, such as images. For example, estimate a person's pose in a video. And the second aspect is generation, which aims to generate new human behavior or motion from existing or observed human behavior data. For example, generate a person's future behavior based on their past behavior. And the third one is simulation, where the goal is to replicate human behavior in a physics simulator. For example, control a humanoid to perform backflips like humans in simulation. In this talk, I will take a holistic approach to human behavior modeling and discuss the three aspects jointly. I will first show how we can leverage generative models to improve human pose estimation. And I will then show how physics simulation can also lead to more physically plausible human pose estimation. Okay, I will first start with human behavior generation for pose estimation and talk about a very special but useful problem of global occlusion-aware human mesh recovery. The task we focus on is global occlusion-aware human mesh recovery, where the goal is to estimate the pose and shape of people in a consistent global coordinate system from videos captured by dynamic cameras. So by dynamic cameras, I mean the camera is constantly moving. And we also want to estimate the pose of invisible people when they are occluded. So here is an example video captured by dynamic cameras. So we can see the person is going in and out of the field of view, but we still want to estimate their pose and global trajectories, even when they are invisible. So the motivation is that first, many videos in sports, movies, and our daily life are captured by dynamic cameras. And second, reconstructing pose in a global coordinate system can enable many applications in AR, VR, animation, sports, and so on. Also, occlusions are a big problem in human pose estimation, especially when people are completely occluded, and traditional method will fail completely in those cases. There are many problems with standard human pose estimation methods when applied to this task. First, estimating the absolute depth of the humans is quite difficult, and even state-of-the-art methods can output jittery or round depths as shown in the video. Second, most methods only estimate pose in the camera coordinates, or sometimes only the root-centered coordinates. So they cannot estimate global human pose from dynamic cameras, since the camera is moving and their pose are not registered in a consistent global coordinate system. Additionally, they also fail to handle severe and long-term occlusions when there is no bounding box of a person for a long period of time. To address all these issues, we propose a new approach called GLAMR that learns to hallucinate invisible human motion from visible data using deep generative models. Given a video from dynamic cameras, we first use multi-object tracking and re-ID algorithms to obtain the bounding box sequence of each person in the video. Once we have the bounding box of each person, we can apply off-the-shelf 3D human pose and shape estimator to obtain the motion of each person, which includes the shape and 3D pose sequence in the camera coordinates. But the motion can have occlusions, where poses for some frames are missing because the person is occluded in the video. So we need to address this. And to this end, in the next stage, we propose to learn a generative motion filler to hallucinate occluded body motions to obtain occlusion-free body motions. Since the motion we estimate is still without global root translations and rotations, as you can see here, these people are facing forward without proper orientation. In the next stage, we propose to learn a global trajectory predictor that infers the global root translation and rotations of each person from their local body movements. So we can see here now the person has different orientations and positions in the global coordinate system. But still, there's one thing missing. We don't have the correct relationships between different people because by now, the processing is done per person, not combining different people and considering their spatial relationships. So in the final stage, we also propose a global optimization framework that jointly refines the global trajectory of each person to match the video evidence, such as 2D key points. So as you can see in this picture, the global optimization ensures that the relationship between humans are consistent with the video. A critical component in our framework is the global trajectory predictor, which can map local body motions to the root translations and the rotations of the person. And the motivation for this is that the body motion of a person is highly correlated with its global trajectory. For example, imagine a person is standing still, then its body pose will not change. So in that case, we can safely assume that the person's root position will not change as well. In contrast, if a person is performing some running motion, then we can also hallucinate that the person's root position will be running forward. And for example, in this video, even though the human behavior is rendered without root translation, we can still perceive that the person is walking backward and taking a step to the left. So humans can hallucinate global trajectory just from local body motion. And we hypothesize that it is also possible to learn a neural network to do the same thing. We learned the global trajectory predictor from a large motion capture dataset, and it maps the local body motions into motions with global root translations and rotations. This step is critical to disentangle body movements from camera movements, because since both the body can move and also the camera can move, so it's hard to disambiguate between body movements and camera movements. So having this global trajectory predictor helps anchor the joint reconstruction of human motions and camera trajectory. Okay, so now let's move on to the qualitative results. Here we show the results of our approach, GLAMR, and the baselines for demo video. So we can see that GLAMR produces smooth and accurate human motions in a consistent global coordinate system. And GLAMR also hallucinates more natural motions for occluded humans, which are rendered in transparent colors. We also compare GLAMR with a state-of-the-art human pose estimation method, HyperIK, on in the wild videos. In this example, even though the person is running, the motion estimated by HyperIK does not move much, while GLAMR can successfully estimate the running motion. This is because HyperIK doesn't take the dynamic camera into consideration, and it's always outputting pose in the camera coordinates. GLAMR can also improve human pose estimation for videos captured by static cameras. Although the pose estimation results appear similar in the camera space, the estimated motion by GLAMR looks much smoother and accurate than HyperIK when viewing from the side angle. Furthermore, GLAMR can also improve the temporal smoothness of the estimated motion. So we can see a lot of jitter in the HyperIK results, which are not present in our method. Here are more results on the popular 3D-PW human pose estimation benchmark. In the video, the bounding boxes are used to indicate whether a person is detected and visible. Again, we can see that GLAMR can estimate more smooth and accurate global motions and infill more natural human motions for occluded humans. Here we can see that the global motions estimated by the baseline are inaccurate, while GLAMR can estimate plausible and natural global motions. Because our method is generative, it can generate various motions for the occluded people. Here we show 4 motion samples for the occluded person. So the network can hallucinate what the person is doing when he is occluded. Now let's move on to the quantitative evaluation. Since there are no public datasets that contain both moving cameras and the ground truth pose information, we create our own synthetic dataset called Dynamic Human Stream 0.6 million. It is created from an existing large human motion dataset. The dataset is synthesized by using a window that moves back and forth to crop the video and to simulate the effect of dynamic cameras and create occlusions. We compare our method against state-of-the-art methods on the synthetic dataset that we created. We can see that GLAMR can estimate smooth walking motions, even with large camera movements and severe occlusions. For quantitative evaluation, we use various metrics to evaluate the accuracy of global trajectory estimation, motion infilling, and the quality of post-reconstruction and smoothness. We can see that GLAMR outperforms the baselines across the board and reduces the global trajectory errors by more than 50%. In conclusion, GLAMR is an initial step towards global human mesh recovery in the wild. An important takeaway is that generative motion models can help overcome occlusions and let us see what's invisible. Furthermore, GLAMR has many future extensions, such as combining the scene information or reasoning about the interaction between people. The code of GLAMR is available at the project website. Besides generative models or the generation aspect in general, can we also leverage the other aspect, physics simulation, to improve human pose estimation? That's exactly what we are trying to find out in the next few projects. We base the foundation of our approach on physics simulation. The reason is that humans live in a physical world. And just like this Paco player, every human's behavior has to obey the laws of physics. And physics simulation provides a way to constrain human behavior to obey the laws of physics. There are many benefits of modeling human behavior in simulation. First, the human behavior output by simulation is more realistic. Second, we can also model human interaction with scene and objects. Additionally, since human behavior is constrained to be physically plausible and always obeys the laws of physics, simulation can lead to better perception and generation of human behavior, especially for out-of-domain scenarios. The first question we want to address is how to represent human behavior in physics simulation. On the left side, a ballet dancer is performing ballet dance moves. To model her behavior in simulation, we first need to create a proxy humanoid agent in a physics simulator. We can then treat human behavior as the result of a control policy for the humanoid. And to successfully model the behavior of the dancer, we need to find a control policy that can reproduce her behavior in simulation. In this way, we have formulated human behavior modeling as policy learning. We employ reinforcement learning, or RL, to solve for the control policy. In the context of RL, our humanoid agent is controlled by a neural network-based control policy that outputs action based on the state of the humanoid. The state typically includes joint angles, velocities, and other context information, such as images. And the action is typically the joint torques to be applied to the humanoid, or target joint angles for PD controllers to compute the joint torques. Once we have the joint torques from the action, we input them to the physics simulator, which generates the next state of the humanoid through simulation. We also assign a reward to the humanoid agent to encourage it to produce the desired behavior. The reward measures the similarity between the policy-generated behavior and the ground truth behavior. We use RL to solve for the optimal control policy, which is the policy that maximizes the total expected rewards, and is also the policy that imitates the ground truth behavior the best, since it maximizes the reward. We can apply standard RL algorithms to solve for the optimal control policy, such as proximal policy optimization, or PPO. Here are some results of the simulation-based human behavior modeling framework. It can learn policies that imitate various human behaviors, such as walking, running, and acrobatic skills. Now I have introduced the simulation-based human behavior framework. I will discuss how we can use this simulation-based framework to improve the perception of human behavior. Specifically, I will first talk about simulation-based first-person human pose estimation. In first-person human pose estimation, we have a person wearing a head-mounted camera, and we want to use the first-person video captured by the camera to estimate the 3D pose sequence of the person. First-person pose estimation has many applications in VR, AR, medical monitoring, sports, training, and so on. However, it is a highly under-constrained problem because the camera can barely see the body of the person. This motivates us to use simulation to constrain the space of estimated pose. We employ the simulation-based behavior modeling framework that we have introduced. The main modification is that now we also input the first-person video to the state of the humanoid agent. So now the control policy is also conditioned on the first-person video. By iteratively executing the control policy in simulation, we can simulate the behavior of the humanoid and get the estimated pose sequence of the person. In this work, we employ generative adversarial imitation learning, or GAIL, to learn the policy. GAIL works similarly as GAN. It learns a discriminator that differentiates estimated pose and real pose given the video. The agent's objective, or its reward function, is based on how much the estimated pose can fool the discriminator. We first test our approach with synthetic data, as we don't have access to paired first-person video and pose. And we synthesize first-person video in the Mujoko simulator using motion capture data. Here we show the results. Our approach outperforms kinematics-based methods in terms of physical plausibility. From the video, we can see that our approach has much less jitter, foot sliding, and ground penetration than the baseline. We also directly test the policy learned with synthetic data on real-world scenarios. As shown in the table and the video, the pose estimated by our approach is more accurate and physically plausible than the baseline. In our follow-up work, we not only want to estimate a person's pose from a first-person video, but also want to generate or forecast their future behavior. First-person behavior generation also has many applications in AR, VR, and medical monitoring. To tackle this problem, we again use our simulation-based behavior modeling framework. This time, we input the past first-person video to the state space of the humanoid agent to provide the context information for the humanoid to generate plausible future behavior. In particular, we use convolutional neural networks and recurrent networks to encode the video into a context feature, which is then used in the state space of the agent and shared by all time steps. In this work, we also improve the physics-based control of the humanoid character, which allows us to achieve much better pose estimation results as shown in the video. So the input is only the first-person video where we don't see the person. And here are some behavior generation results of our approach. So based on the first-person video, it can forecast whether the person is going to walk forward or crouch, or and do these different things. Besides first-person human pose estimation, our simulation-based behavior modeling framework can also improve third-person human pose estimation. Third-person human pose estimation has been studied extensively. However, most state-of-the-art approaches are kinematics-based, which means they model human motion without considering the underlying physical forces. Although these methods can often achieve high pose accuracy, they often have physical artifacts such as jitter, foot sliding, and ground penetration, as shown in the video, which prevent many applications such as animation, VR, and medical analysis. To address these issues, we propose a simulation-based third-person human pose estimation method called SimPoE. It integrates both kinematics and dynamics modeling to achieve accurate and physically plausible pose estimation. The core of our approach is a recurrent kinematics plus dynamics module that performs both kinematic reasoning and physics simulation. Inside the kinematics plus dynamics module, we have a kinematic pose estimator and a key point detector to obtain initial pose estimates and 2D key points, which are then input to a kinematics-aware policy to output control actions. To put our method in the context of our simulation-based behavior modeling framework, we first added kinematic pose and 2D key points to the state space of the agent, and we also make the policy kinematics-aware to effectively utilize the kinematic pose and 2D key points. The kinematics-aware policy has a kinematic refinement unit that iteratively refines the kinematic pose based on the matching of 2D key points. It also has a control generation unit that uses the refined pose to generate control signals. Both the kinematic refinement unit and the control generation unit are learned jointly with RL. Now let's take a look at the design of the reward function, which is similar to the loss function in supervised learning setting. We use several rewards to match different aspects of the estimated human pose sequence with the ground truth. In particular, we design rewards that try to match pose, velocities, 3D joints, and 2D key points. Our humanoid agent is created automatically from human mesh models such as SMPL. We use the skinny weight matrix to obtain the vertices belonging to each bone, and we then compute the 3D convex hull of the vertices to get each bone's geometry. Now let's look at the quantitative results of our approach, SimPoE. On large human motion datasets, SimPoE beats both kinematics and physics-based methods in both pose-based and physics-based metrics, such as acceleration, foot sliding, and ground penetration. In particular, SimPoE outperforms prior physics-based pose estimation methods significantly. Here we show qualitative results of SimPoE. We can see that SimPoE has little artifacts compared to kinematics-based method and produces more natural and realistic human motions. So here we can see a sharp pose change for the baseline Y, which does not happen for SimPoE. In the next work, we also extend the simulation-based framework to estimate human-scene interaction. In this project, we again focus on the first-person setting, where we use videos from head-mounted cameras to estimate the person's pose and their interaction with the object in the scene, such as sitting in a chair as shown here. The key component in our approach is a universal humanoid controller that takes as input a target pose and outputs the necessary control to achieve the pose in the physics simulator. The universal humanoid controller is trained on a large motion database in mass without any visual inputs. And the second key component in our approach is a dynamic regulated kinematic policy that uses visual inputs and the current simulation state to output the target pose for the universal humanoid controller. We also have an initialization module for estimating object pose and image features from the video. Here we show qualitative results on a test MoCap dataset. We can see that our model performs well on various motion types. So here we show the sitting motion. Previous methods have very large root drifts and low success rate of human-object interaction. Here are results on the real-world dataset. Note that our method is only trained with motion capture data, and it can still generalize to some real-world scenarios. So far, I have talked about leveraging physics simulation and generative models to improve human pose estimation. So we essentially explore the synergy between simulation and perception, as well as the synergy between generation and perception. A natural question that may arise is that, can we also explore the synergy between simulation and generation? That's exactly what we did in the next project, where we use physics simulation to guide human motion generation. There have been a lot of recent success in diffusion models. They have also been applied to human motion generation and achieve great results. State-of-the-art human motion diffusion models can generate diverse and realistic motions while also allowing motion editing and infilling. However, diffusion models still cannot ensure physical plausibility, so their motions can have a lot of artifacts such as floating, penetration, and foot sliding, which limits their applications. As we can see here, the motion here is the hands are penetrating the ground, and sometimes there are foot sliding of the person. To tackle this issue, we propose an approach that enforces physical constraints in diffusion models. So as can see in the results, our method ensures proper contact with the ground and reduces penetration, floating, and foot sliding. Here is a high-level comparison. Here is a high-level comparison of our approach with the prior work. State-of-the-art human motion generation models use denoising diffusion directly to map noise and conditional information such as, the video has some sound, okay. However, since the diffusion process disregards the laws of physics, the motion they generate can have pronounced artifacts, such as foot sliding, floating, and ground penetration, as highlighted here. In contrast, our physics-guided diffusion model, PhysDiff, addresses this problem by embedding a physics-based motion projection layer into the diffusion process to enforce physical constraints. The motion generated by our model does not have the physical artifacts often observed with state-of-the-art motion generation models. And here is an overview of our model, PhysDiff. It leverages a series of physics-guided motion diffusion steps to map noise and text into the generated human motion. And in each physics-guided diffusion step, a denoiser network is used to first denoise the motion into an estimate of the clean motion. We then use a physics-based motion projection module to project the denoised motion into a physically plausible motion. Specifically, the projection module uses a motion imitation policy, similar to the policy that we use in the human pose estimation task, to control a character in a physics simulator and to mimic the input motion while also enforcing physical constraints. The motion produced by the physics-based projection module is then used to generate the motion for the next diffusion step and further guide the diffusion process. So here are the comparison with state-of-the-art human motion diffusion models. So as we can see, our method has much less floating and ground penetration and much better contact with the ground in general, and less foot sliding. And here are some more results of our method for various text prompt. To summarize, physics simulation provide additional constraints on human dynamics, which enables better human pose estimation and generation. And second, RL is an important tool for solving non-differentiable problems, such as those involving physics simulation. The main takeaway from this talk is that human pose estimation is often an under-constrained problem. And there are often problems such as depth ambiguity and occlusions and moving cameras that make the solution not unique. In this talk, I have showed that leveraging data-driven priors such as generative models trained on motion capture database can help. Or we can use the laws of physics as prior to improve the physical plausibility of the estimated pose. However, there are also many open challenges in this area. The first one is that there is limited human pose data to train generative models. And because of limited data, it is hard to train a highly generalized generative model, such as, for example, compared to those large language models. And second, physics simulation of humans is often oversimplified for both because of the capacity of the simulator, or often due to the efficiency required by a reinforcement learning algorithm. So too complicated model can significantly slow down the training time. And because of this oversimplification, there's no, for example, no muscle is modeled and no soft tissues are modeled. And so sometimes this can lead to some inaccuracy in the simulate, or like some behavior you just cannot simulate from using the current simulator. But that being said, using a simplified model can still improve the physical plausibility of the estimated motion, because we are also learning a network model that can absorb the errors in the simulation. So the control policy that we learned, it can learn to adjust to the model, but still output the desired motion and match the ground truth data. So we can still leverage the inductive bias provided by physics simulation. And the third takeaway is that a third open challenge is that learning to control humanoids in simulation with reinforcement learning is hard, and it is often very inefficient to train these controllers with RL. And a potential solution is to use differentiable simulation, which could make learning much more efficient. However, many of the existing differential simulators still have limited functionality and robustness. So this is still like a very active research area, but I think it is a promising direction for learning to control humanoids, and further for the task of human pose estimation or motion generation. Okay, yeah, thank you. This is the end of my presentation, and I'm happy to answer any questions.
I had a question about the performance. Once the models are trained, can they be applied to real-time pose estimation in order to improve the quality of, to reduce noise and make it more physically plausible?
Once it's trained, can it be applied to interval data?
Yeah, so if you have a pose estimator that looks at a humanoid and gets the joint angles and everything from that, gets a rough estimate of that, can this be used to smooth it and make it more physically plausible? Or would it have to be trained all together?
Yeah, you don't need to retrain it altogether. So, for example, in this project, we have this universal humanoid controller that's taking in some kinematic pose. And it could be like a very rough pose estimate. And it can have many like physical errors. And And this universal humanoid controller can learn to correct those errors because, because it goes through the physics simulation.
Could it do it at 30 frames a second?
30 frames a second?
33 milliseconds, yeah, per frame.
Yeah, I think so. Depends on how fast is the simulation. Yeah, but I think it's possible, yeah.
I have two questions. Let me turn my video on. Yeah, I was, hello, by the way, so excellent talks, amazing stuff. I was one of the first visual effects supervisors that did optical motion capture in the early 90s. And so I'm very familiar with a lot of the problems associated with it, but I have two very poignant questions for me. I've been working in the using, generative diffusion model art quite a bit the last 6 months. And do you envision at some point you'll be able to do embedding, be able to train like for a specific character? Like if I'm doing, Batman or Shrek, I can do a simple training on that character and then have the simulation be now able to react as those characters would, right? Because I can do that with generative art right now. I can embed myself or whatever character into it.
Yes, so if I understand correctly, you are saying whether we can embed the character in the physics simulation and see how they will perform in the simulation?
Yeah, because in the diffusion model for visual art, for example, you can, let's say I want to take your face and train it. It takes very little time to train it, and it'll diffuse towards your face, no matter even put whatever pose is at, right? So there's a very simple method of embedding a specific character or multiple character. And do you foresee doing the similar thing with your PhysDiff in that way that you'd be able to build embedding into the system so you can train it for a specific character, right?
Yeah, that's interesting. Yeah. But I think it's harder for physics simulation because essentially if you have the dimension of, for example, the skeleton of the character,
Yeah.
then you can already simulate like how you will react in the simulation. I guess maybe your question is more towards, can you, for example, the analogy would be if you give me the motion of a person.
Exactly. Like a specific actor of a certain walking gait pattern, right? So I want to train it to be like, let's say I want to do, whatever famous actor you happen to be using in this game or something. I want to be able to train it with that behavior of that actor, right? So that's an embedding of a behavior in a diffusion model, right?
Yeah, I think so.
Okay.
Yeah, I think that's a good idea. Yeah.
Second question, go back to when I first did MoCap back in the early 90s. We were like jumping up and down if we can use physics simulation to do motion capture and we can do this amazing animation. But then the first problem I ran into was when the director looked at my work and he said, oh, this is all great, but on frame 23, I want him to reach out a little bit further. He wants a direct emotion. How do you see we be able to add the ability to direct motion?
Yeah. So if I understand correctly, you want to edit the captured motion, right?
Right, right. Be able to come in afterward and say, hey, when he fall down, I want him to hit his head instead of land on his face, right? Be able to come back and modify the motion.
I think it's possible. I think it's possible through, for example, motion infilling or motion in betweening. So maybe you just remove some part of the motion and you add some keyframe and modify that keyframe a little bit, right?
Okay, so
So,
still
for
back to
example,
still traditional method of modifying the data and reiterating on it. So, okay, that makes sense. Interesting. Well, thank you. That was a wonderful talk.
Yeah, thank you so much.
There any other questions?
Yeah, I guess I was wondering along the same line, could you actually have it watch the movie of the character and and you know, be it a superhero or whatever, trying to go beyond the regular physics? Could it learn a different sense of physics by watching some other character, so you could create that?
Yeah, I think that's also an interesting direction to explore. So I think if you have, maybe if you have large enough amount of data and large enough models, you can learn this generalized physics simulator. So for example, for those like stable diffusion models, if they come up with like more advanced video version, if like they can already simulate the person doing all kinds of stuff and very realistic and very physically plausible, the model itself already has learned the laws of physics. So I think it's definitely possible if we have large amount of data and yeah, and correct training of the model.
Do you think it would be possible to have a parameter such as body mass and be able to adjust that with the slider to change from one kind of character to another?
Yeah, I think it's possible. I don't know if you have seen the control net. So I think using a similar approach, like fine-tuning the, for example, fine-tuning the model that we just mentioned, like for example, like a motion diffusion models, and on different characters with different mass, and you can then just adjust the mass, and you can get different results. Yeah. So I think there is a lot of parallel between the image domain and the motion domains, and advances in the image domain can also definitely inspire the things in the motion domain. But the motion is also, I feel it's also sometimes harder because the temporal dependency and the temporal like nature of the problem.
Thank you.
Yeah, thanks for the questions.
So it seemed with some of those camera ones, you know, even had a nice rectangular pattern for the ground, but so it's just having trouble mapping the humans. I mean that not your method, but I mean that they're having trouble mapping the humans in 3D space to keep them on the ground. Is that, I know you're solving that problem, but what was causing the confusion before from that image?
Which image? You mean the egocentric input?
Well, you had like the dancers on, and it was like a regular pattern on for the ground, you know, the brickwork, and it just seemed like it'd be so easy tracking that information, but it's the humans in 3 space that's a problem, and that's why they go flying. Or
oh, you mean this the PhysDiff up here?
well, the dancers you had in the very beginning.
Oh, you mean here? Oh, here. There, right?
That one.
Yeah, I think it's a little difficult to. I guess you can always just try to put the person on the, like for example, put the lowest point of the person to the floor, but it still wouldn't be very or like it still wouldn't look very good because it can fly all around because the pose is very jittery, and so I think maintaining proper contact is kind of hard, and we are not using any tracking here, so it's just the flat ground. So we're not mapping the environment.
Very impressive, all what you've done there and all those pieces, putting them together.
Thank you.
Quick question. Where do you see the next big hurdle for you to overcome?
In terms of human pose estimation?
Yeah, in this whole palette of amazing work you guys done, what are the next set of hurdles?
I think mainly like considering the scene and object interaction. Those are the hard things, and also fingers. Because if we want to capture like the motion and in relation with the scene, we have to reconstruct their interaction well. So I think that's the biggest problem for us now.
So for something like catching a football and blocking a person by playing football, that would fall into this hard category. Is that right?
Yes. Also, like interperson interaction. Like if you want to estimate two-person dancing or hugging, it's very hard because there are so many occlusions, and it's also easy to confuse one person's 2D key points with the other person's 2D key points. So yeah, those problems are very, very hard.
So like the scrimmage line on a football game where everyone's piled up there at the.
Yeah, those problems is very hard, yeah.
I was hoping it would somehow help resolve it, because you do have the physical separation, the reality there that it might be able to figure out some of it. But yeah, I guess it's you're missing information and you can't tell, right?
Yes, and from some point you will need the generative model parts. So I think to fully solve it, you need to combine the two, because if you have a powerful enough generative models, like similar to like how human would hallucinate motions when you see, for example, the football scenarios you mentioned, then it's all about like hallucinating plausible scenarios, because there is no like one correct answer for those motion, because you can't see them. But you can definitely imagine what's the most possible scenarios for the motions, for the pose of each like occluded person. And adding the physics prior will just ensure that those hallucinations are also physically plausible, and it just further constrains the problem.
I mean, you'd have to also throw in the fact, like, when you see them injure themselves, in some way, that they're deforming beyond the expected, behavior of the human model.
Yes. Yeah, that's right. Yeah. I guess arguably in the end, you can say like everything is kind of like a generative model. And even the physics, maybe you can learn it through generative model. But I guess the good thing about physics is that it's always, you don't need to learn it and it's always correct. But with generative models, it's limited to the training data. So unless you have a very large amount of training data, and the data is general enough, then you can possibly train a very general generative models like Stable Diffusion and Chat GPT.
Well, maybe if there's no more questions, I don't know whether you have pointers to your papers that other people can look at.
Yeah, I have. So how do I share?
You
I can type in the chat.
into the chat. That would be a good place. Or if you have a website that people could access.
We did have that in the description, also, your website.
Yeah, I have. So many of these works are covered in the website, and also you can, if you're interested, you can also take a look at the my PhD thesis. So it summarizes all these works.
Oh. And the link to that website was in the meeting notification. Or oh, you've got it. You put it in the chat.
Yeah, I sent in the chat. Yeah.
Okay. Fantastic. All right. Well, thank you very much, Ye. And we invite everyone else to join us for the next meeting. Alesh, was that on March 15th?
Yes, it's March 15th will be our next joint meeting was the ASIM chapter.
And there was another March
And
meeting as well?
I think it was, yeah, and also there'll be March, I think it was the 29th, I think.
Yeah, 2 weeks later.
2 weeks later.
Great. So it's going to be an active month.
Right, yeah. It'll be we'll have 2 VR meetings next month, so it'll be a good time for VR. Thanks for the great presentation, and we really enjoyed having you come to the chapter and give a talk. So
Yeah, thank you for inviting me. Yeah, it's fun.
Thank you, Ye. Bye.
Thank
Thank you.
you. Bye,
you.
everyone.
bye.